Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers. Hello there, ladies and gentlemen. Welcome back to the Ephemeris podcast. I'm your host, Felian. Thank you for joining me on another episode in this new chapter of the podcast where we are looking at news in the world of astronomy. And if you're new here, that's the premise of what we're doing here. The structure goes as follows. We look at three articles that sort of explain some new findings that have been uncovered. And the first article for this week is going to be about the dwarf galaxy children of an amateur astronomer. Not literally, but in name. Why don't we say that? Um, The second article that we're going to be talking about is stars collapsing into black holes seemingly out of nowhere. And the last article will be about a nuclear star cluster. So, yeah, with that out of the way, let's get right into these stories here. Sit back, relax, and enjoy. So, first article that we have here, amateur astronomer finds 5 fascinating new galaxies, and they're now named after him. So, Giuseppe Donatello, hopefully I'm saying that correctly in a, like a acceptable accent because I have been studying Italian a little bit. So this guy's an amateur astronomer and astrophotographer from Italy who, over the last few years, has discovered some of his own celestial objects, and they include 5 dwarf galaxies that surround the Sculptor Galaxy. And I believe the Sculptor Galaxy, is a distant and early galaxy. So, yeah. The first of these 5 galaxies was discovered in 2016 through Donatello's photographs, and the newly discovered conglomeration of dwarf galaxies joins 3 other galaxies that are around the Sculptor Galaxies that Donatello has discovered. And so 9 of the 11 major objects in this region are actually named after him. The 5 most recent objects, they've been named Donatello 5, 6, 7, 8, 9, respectively. And so, I mean, for an amateur astronomer, this is very significant because it's usually all the professional astronomers that get the rep for finding all these celestial objects. They do the research, they're in the labs, and once they make these observations and do, studies in length about the objects, I think, generally they do have the honor of naming them. But with amateur astronomers, I mean, amateur astronomers are usually not doing such, in-depth work, so credit is not so much given towards those hard workers. But here, I mean, we have an amazing story about someone who did the work to get, dwarf galaxies named after him. So, yeah, pretty amazing. Other than that, though, there are some amazing features about the dwarf galaxies that we're talking about here. They're satellite galaxies around the Milky Way galaxy. And what's interesting about satellite galaxies for the Milky Way is that only recently have we, raked up a bunch of new dwarf galaxies that we found, satellite galaxies that we've found around us. The number has gone up 5-fold, from 12 to about 60 since 2004, which is only 20 years ago. And I should add that current galaxy formation theories, they propose dark matter halos and gravitational wells across the universe that attract the material, like neutral gas, to form major galaxies. But not only major galaxies, also the regions surrounding galaxies should have similar features, like dark matter halos. But we have not observed as many satellite galaxies as the current model of the universe, the Lambda CDM model, predicts. And it actually predicts like thousands of satellite galaxies around Andromeda, and definitely more than 60 satellite galaxies around the Milky Way, but we just have not found them yet. So what Donatello is doing here is discovering a lot more of these satellite galaxies we should be seeing, and he's really doing the model a service, because otherwise, there are revision efforts that have to be made to Lambda CDM, and cosmology is already complicated as is. So yeah, if you hear about the work he put in as well, which is described in this article, you'll really appreciate what he's doing here. Quote, to investigate whether LCDM models may need revision or if efforts need to be upped to hunt dwarf galaxies around larger galaxies, Donatello and team turned to archival data collected by the Dark Energy Spectroscopic Instrument located on the 4-meter-mile telescope at Kitt Peak National Observatory. Donatello and colleagues specifically focused on its observations of the Sculptor Galaxy and its vicinity. This study led to the discovery of 8 dwarf galaxies in the Sculptor Galactic Group, as we kind of talked about. The team revealed 3 of them in 2021 and the other 5 more recently. Astronomers now know of 18 galaxies in this grouping around NGC 253, including NGC 247, discovered in 2011, and some dwarf galaxies of greater mass. So, yeah, I mean, this is a lot of very, very hard work that's going into the research here, especially coming from an amateur astronomer. And lastly, to top it all off, Donatello had some, I would describe, bold words for what lies within the galactic group. So, here we go. Quote, even more extreme objects have recently been found made up of a few dozen stars, which we struggle to define as galaxies, but more properly as halo clusters. Donatello said, sorry. There are likely hundreds of such star systems waiting to be discovered. There is still room for more discoveries. However, the DESI data may not be deep enough to find new low luminosity candidates. So, I mean, Donatello clearly knows his stuff here. Talking about the definition of halo clusters and how sort of they're very low luminosity and there's more depth to the analysis that needs to be utilized. So, yeah, I mean, this guy's a real G, I guess you could say. I don't know. I'm trying to use modern terminology. I don't know if it is exactly suitable, but whatever. So, yeah, that is the amazing story of Giuseppe Donatello. And we will now move on to our second story here, which is about vanishing, collapsing stars and how they might just be forming into black holes on their own with no extravaganzas going on. Why don't we put it that way? I don't want to reveal the details in the beginning because we will talk about them in just a moment, but that is the gist of what we're talking about with this second story. So, if you're familiar with basic astronomy concepts, you'll know that stars that are several times larger than the sun are bound to collapse after a supernova, and they will then enter the end of their life cycle. So, you can have let's say a star that's like 9 solar masses, and it goes through a type 2 supernova event where it's like a core collapse. There's a huge explosion, and then perhaps it turns into like a neutron star, or if it's a little bit larger than that, or probably if it's a little bit larger than that, maybe it could collapse into a black hole after going through that type 2 supernova. But what if I told you that it might be possible the stars can skip the supernova phase and instantly turn into stellar remnants? It seems that's what we found, and some Danish astronomers at the Niels Bohr Institute in Copenhagen have analyzed a binary star system that vanished on its own with no dramatic supernova exit. They looked for asymmetry typical in supernovae and neutrinos, but nope, they did not find any evidence of a supernova. A quote from the article that describes some of the features that weren't seen goes as follows. Quote, for example, the orbits of the star and the black hole in VFTS 243, which is the name of the celestial object, around their common center of mass are still nearly circular. However, supernova explosions are asymmetric, with a little more energy produced in one direction than the other, which should give the compact object, uh, that forms a quote-unquote natal kick. Such a kick would accelerate the compact object, causing its orbit to widen and become more elongated. Typically, this kick is between 30 and 100 kilometers per second, yet the black hole in VFTS 243 has, at the most, been kicked by just 4 kilometers per second. I sincerely apologize if you all hear the yard work in the background. I'm going to try my best to suppress the background noise, but it's just really loud outside. So anyways, let's talk about what we've discovered here. So we discovered that the orbits are perfectly circular, or nearly circular, even though they should be slightly elliptic, and they shouldn't be, symmetric. So that's interesting. Do we have any good answers for what they've seen, or is their guess as good as ours? Well, immediately there's an answer, or sort of a hypothesis, that goes towards a simple review of stellar dynamics. So our understanding of black holes is that they form due to the gravitational collapse of an overwhelming amount of mass in one point of spacetime. So really, the only trigger that we know of, or threshold, or the prerequisite for black hole formation that we know, is the gargantuan mass of a system, or any given system. But the formation of a supernova event is slightly more complex. It's where either mass accretion by a star in a white dwarf binary creeps up to the point that an outburst occurs, or the mass of a large star floods the core and causes an outburst. Right? Those are the two types of supernova. So, that would be the process in a nutshell for either type, respectively. So the suggestion here, with our immediate sort of hypothesis, is that stars accrete matter so fast that a gravitational collapse occurs before an outburst. And so the term that's given for an event like this is a quote-unquote complete collapse. And the object observed by the astronomers is not the only candidate for such an event, which you might expect because of how revolutionary this sounds, but really there's a number of complete collapse candidates that we just did not have any sort of theory for, I guess you could say. There are hundreds of stars that have disappeared in recent years that lacked explanation, but now that we've looked at a binary system in detail and discovered these details don't really match what is expected, I think we're leaning more towards this sort of postulate or hypothesis that could explain all of these other unexplained findings about stars. So yeah, we could have brought some resolution to this issue here, but we do have some other issues to deal with. The writer of the article here describes, quote, "There are also wider repercussions. A supernova explosion is an element factory. However, if some massive stars are collapsing completely into black holes without supernova explosions, then they cannot contribute to the creation and recycling of elements. Cosmochemists will thus need to factor this concept, if it is indeed true, into their models of how elements are formed and spread across space." So yeah, that is very interesting. I don't know exactly where that's going to fit. I think a lot of our investigation of, sort of astronomical chemistry lies in just looking at different populations of stars and again supernovas. So yeah, I think this is a very intriguing concept, and it definitely requires further study, that's for sure. So with that out of the way, let's get into our last article today, which is a little bit more dank. Hopefully I don't throw anybody off by using the word dank, because it's pretty I guess it's a pretty Gen Z term. But either way, the article sort of brings us back to the Milky Way and its center rather than its outskirts. So we're talking about some peculiar phenomena occurring near Sagittarius A star, which is the Milky Way's central black hole. The article itself has some pretty wise words for what goes on near Sagittarius A star, so I'm just going to let it speak for itself. Quote, Sagittarius A star's overwhelming gravity creates a chaotic region where tightly packed, high-speed stars crash into one another like cars in a demolition derby. Which, yeah, that's one way to put it. And it continues, quote, these collisions and glancing blows change the stars forever. Some become strange, stripped down, low-mass stars, while others gain new life. But it's not only the speed that drives the collisions. The region is also tightly packed with stars into what astronomers call a nuclear star cluster. The combination of high speed and high stellar density creates a region where stars are bound to collide. Nuclear star clusters. Never heard of them, so let's find out a little more. So, first of all, nuclear star clusters aren't literally nuclear. They're just highly luminous and very dense, so it's almost to the point that they seem nuclear, quote unquote. They're very typical in galaxies, especially at the center. They show up a majority of the time in pretty much all galaxy types and are usually in the center of them. But check this out. Quote, NSCs are the densest known star clusters in the universe, with apparent magnitudes between -14 and -10 magnitude in the infrared. They're on average 40 times brighter than globular clusters, although their effective radii are not larger than 2 to 5 parsecs. With a dynamic mass of 106 to 108 solar masses, they are at the upper end of the values reached by globular clusters. So these things are more massive and more bright than globular clusters, which, I mean, globular clusters are quite the celestial objects in our universe. And, I mean, -14 is almost unimaginable in terms of brightness, because, wow. Like, I mean, if you understand anything about the magnitude scale, you'll understand what I mean. If you're not familiar, I believe it's a logarithmic scale, and the lower your number is, the brighter an object is. So when you're getting to -14, that is really, really bright. And the effective radius being 2 to 5 parsecs, I mean, that's insane. You're getting like probably millions of stars within about like 10 to 15 light years. So, I mean, the numbers speak for itself. The number speaks for itself. So, anyways, that brings us to the nuclear star cluster that is in our cosmic backyard, now that we understand what nuclear star clusters are. So, why are we describing it like, this nuclear star cluster is driving collisions like a demolition derby? What's up with all this a fancy language here? So, the density of the cluster itself makes the region around Sagittarius A extreme. There are almost 1 million stars within 1 parsec of each other with lots of energy, and they're colliding. So what we're saying here is that the environment we observe around Sagittarius A star is not necessarily chaotic because there's a supermassive black hole that accelerates these stars to really high speeds, but it's also because it's a very dense region, which will necessarily cause more collisions between stars. So, yeah, that's not even the most special part about it, because I think, that's a little bit easier to digest. The result of this chaos here near our supermassive black hole is very notable. Researchers were running a simulation of the nuclear star clusters and found some really weird occurrences. I will quote from the article itself here. The simulation showed that head-on collisions are rare, so stars aren't destroyed. Instead, they're more like glancing blows. where stars can be stripped of their outer layers before continuing their trajectories. So it's kind of like when we talked about galaxy collisions, where it doesn't necessarily cause destruction, but it's like rather deformations a little bit, and instead of it being galaxies here, it's actually stars. And I think that makes for interesting stellar evolution, if you ask me. I will also bring in some quotes from the lead author here. They whack into each other and keep going. They just graze each other as though they are exchanging a very violent high five. This causes the star to eject some material and lose their outer layers. Depending on how fast they are moving and how much they overlap when they collide, they might lose quite a bit of their outer layers. These destructive collisions result in a population of strange, stripped down, low mass stars. A few stars win the collision lottery. Through collisions and mergers, these stars collect more hydrogen. Although they were formed from an older population, they masquerade as rejuvenated, young looking stars. They are like zombie stars. They eat their neighbors. So, yeah, I think this is, what the lead author has described here. Really, it's a description of a very interesting region of space where, I mean, you could say stellar evolution, or, like, its very common types are probably thrown out of the window. And my curiosity would be if it's like possible to classify some of these stars as like Wolf-Rayet or blue supergiants, or Wolf-Rayet. I don't know. Either way. So yeah, I think very interesting region of space. I'm actually quite happy that I found out about it. And yeah, I mean, a region like this could tell us more about the extremes of stellar evolution. What would be extra dank is if we could uncover some really offbeat evolutionary pathways for these stars that are involved in high density regions, but that's me going on an unnecessary tangent. So, yeah, that's all we got for today's episode. Hopefully, you all enjoyed listening to some of these stories here. I especially liked the last one. That was one of my favorite ones. It was a little bit straightforward, but also a little bit like, drove a little bit of curiosity in me. So, yeah, let me know what your favorite story for today was, or for this episode was, in the comments if you'd like to. And if you all enjoyed listening to this podcast episode, which I assume you did, considering you made it to the end, I would sincerely appreciate a subscribe on YouTube if you're listening there, a follow on Spotify if you're listening on Spotify. And yeah, hopefully I'll get back to a more regular uploading schedule. I know I had to delay this episode a little bit because I was sort of chillaxing, I'll say, because I did have a busy week last week. But yeah, that's besides the point. I will get back to a regular uploading schedule and hopefully make up for some of the missed episodes over the last couple of months. So yeah, until the next episode, I will see you all later. Peace.